Hi, welcome back. In this lecture, I will describe the finite difference time domain method. This method combines finite difference both in space and in time. So the finite difference time domain, in short FDTD, is one of the most popular computational methods for microwave problems. And why is that? Well, the FDTD is simple to program, highly efficient, and easily adapted to deal with a large variety of problems. The FDTD scheme is typically formulated for a structured Cartesian grid, so quite simple grid, typically are uniform and quite structured, so the grid spacing is always the same. And it discretizes Maxwell equation formulated on the time domain. The FDTD combines finite difference both in time and in space. So we take the derivative with respect to space and time, and we approximate this by finite differences. In finite difference time domain methods, the field components of the electric field and magnetic field are staggered in space with respect to each other, in a particular manner that is tailored to the Maxwell equation. We will discuss a little bit more about this, in particular about the E lattice. So what is the disadvantage of FDTD? Well, the disadvantage is well depicted on the slides, where we try to describe a curve on a uniform Cartesian grid, and you see that introduce this kind of approximation that is called staircase approximation. So a major weakness of this method lies in the way it deals with the boundaries that are not aligned with the Cartesian grid. So for instance, this issue comes up with oblique boundaries of curved boundaries. And the FDTD programs typically resort to the staircase approximation. So we just approximate the curve as a staircase resembling a grid for the boundary. We will see in the third module of this course that the finite element method, FEM, is much better suited for problems with oblique and curved boundaries, and find structure that might need a higher resolution locally. So we might want to have increased resolution only in certain part of the domain. So what are the advantages? Well, first advantage is simple, and the second advantage is that is quite efficient. And the reason for that is that it allows for explicit time stepping and makes the method much more efficient than the time domain finite element methods that we'll see later on, which is in general implicit. That means that it requires the solution of a linear system that is quite expensive to compute. Another advantage of the FDTD is that no matrix is needed to solve the FDTD scheme. So the fact that we don't need a matrix to be stored reduces memory consumption and make it possible to solve problems with a very large number of unknowns, since we are now storing the full matrix. We will see that one of the constraints on the FDTD is about how we choose the time step and the grid spacing. We talked before about the Courant condition. So the FDTD method has a time step limit, also called the Courant condition or CFL condition, that says that the time step that we are choosing for our simulation must be less than the grid spacing divided by c, that is the propagation speed of a certain signal. C is the speed of light. That is the major propagation speed present in electromagnetics problem. So this introduces a limitation on how we choose the maximum time step. And this is a major limitation in problems involving timescale that are much longer than it takes a light wave to cross all the simulation region. This means that we need to resolve the propagation of the light wave very, very finely in order to have the method scheme. If we have a phenomenon, like for instance, we are interested in modeling eddy current problems, then the time step might be too small to follow some phenomena that develop over quite large time scale. So the FDTD algorithm was introduced in the 60s, originally proposed in a paper by E. You see here on this this slide, in 1966. The literature on the FDTD is quite vast and basically encompasses a large period of roughly 20 years, going from 75 to 95, that show and publish many numbers of research papers where the method was largely improved. So the number of papers exponentially grew in time. So a very famous book that you might want to consult about finite difference time domain is the books by Taflov and Hegnes, that gives a good overview and describes many important extensions of the finite difference time domain numerical technique. In this lecture, we are going to solve the 1D wave equation numerically. So we will resort to the usual approach. We divide the space axis, in this case the z-axis, in intervals of length dz. So dz will be the grid cell size. And also we discretize the time into intervals of dt. We call r the index that refers to the z coordinate. So we will have r for the z coordinate, r plus 1 for the next z coordinate, and r minus 1 as the previous space coordinate. And we will use n to refer to the time coordinate or the time level. So here as an apex. We saw this before, that we can discretize the 1D wave equation by using standard difference approximation for derivative. In this case, we have two second-order derivatives, and we use the usual formula to calculate the second-order derivative for the time domain and the space. From this equation on the slides, we can find an expression for AR, so the electric field at one point at the next time step, that is n plus 1. So the equation that we found is simply an update of the values of the electric field at the previous time step, or the previous time step, so n and n minus 1. And it will also include the values at the time n of the neighbor electric field values. So one important thing that we need to notice is that when we solve a second order equation, we will require as initial condition two time levels. So not only we need to provide the electric field at a certain time, but also the electric field at the previous time step. So two time levels of the electric field must be given as initial condition. This is analogous for the solution of the analytical wave equation, where we need E, but also we need delta E over delta t as a function of z at the time equal to 0. So we want to understand how good is the numerical FDTD and what are the numerical properties. So what we're going to use is the usual complex exponential analysis that we have been used before to derivate the numerical properties, in particular the numerical dispersion of the equation. So we saw that whenever we discretize, we also add a dispersion to a given way that is not physical but is numerical. So it's important to evaluate what is the impact of the numerical scheme on the properties of the propagation of our wave. So as we did before, we take our initial discretized equation, that is the one from the previous slide. We plug in an expression for E, R, N using the complex exponential. So here we replace it. We replace this two expression in the form of a square equation from here to here. And then we take the square root of this equation. Applying the formulation, this expression here and this expression here are equivalent to the sign, to the exponent of this imaginary complex exponential. And we determine this dispersion relation for our 1D wave equation discretized with the center difference. So this is the final dispersion relation that we find for this problem. So for the numerical solution, the angular frequency omega is only approximately the linear function of the wave number k. So this is only linear if this factor here, c multiplied by delta t over dz, is equal to 1, right? So if apply our cosine here and here, this is 1. Here we will get omega equal to plus minus c multiplied by k. That is the analytical solution. However, this is the addition of our numerical artifacts. So what it means that we are introducing a numerical dispersion relation? Well, that means that waves with the different wave numbers will propagate with different velocity. So not all the different wave numbers will propagate with the c velocity. In particular case that we have a wave package that contains several different spatial frequency, the change of our signal will change as it propagates. So there will be dispersion of different spatial frequency according to the dispersion relation. The formula that we derived in the previous slide allows us to talk about numerical dispersion and stability. So how does the choice of delta t and delta z affect the dispersion equation? So we already commented for the previous slides that this factor here is very important. So this equation shows that this important parameter c multiplied by delta t divided by delta z, that we are going to call r, describe how many grid cells the exact solution propagates in one time step. So it means that if r is equal to 1, we will have only one cell that exact solution propagates in one time step. So if r is less than 1, it means that the signal propagates in less than one cell. So it's just a fraction of one cell. And most importantly, if r is greater than 1, it means that our signal will propagate more than one cell than per one time step. And this is a plot of our numerical dispersion relation. So we see that for r equal to 1, we get a straight line, so there is no dispersion. This is equal to the analytical solution. We see also that for r less than 1, we are going to have a dispersion for the higher spatial frequencies. So how do we choose the time step? So when r is equal to 1, our time step is called the magic time step. That means that the signal propagates exactly one cell per time step. If r1 is equal to, if r is equal to 1, then also delta t is equal to delta z over c, and r is equal to 1. Our equation, our numerical expression, simplifies to omega equal to plus minus speed of light multiplied by the wave number. It is exactly an analytical dispersion relation for electromagnetic waves propagating in the vacuum. When r is equal to 1, the corresponding delta t, the time step, is called the magic time step. And this magic time step doesn't show any dispersion. Let's look at example when we have r less than 1. Well, in this case, the numerical dispersion relation differs from the analytical. You will see that it's banded for high frequency, spatial frequency. So the smaller is r, the stronger is the numerical dispersion. So we will bend it up, and you will see that different spatial frequency will propagate with a different shape. So dispersion properties improves as dt approach the magic time step. That is the time step for which r is equal to 1. So what happens when r is greater than 1? then our original numerical dispersion relation yields complex angular frequency for wave number such that this expression is greater than 1 over r. As a consequence, some waves will exponentially grow in time, and the algorithm is unstable. So when c multiplied by delta t is greater than the grid spacing, the signal of the true solution propagates more than one cell per time step. And this is not possible with the explicit scheme, which involves only nearest neighbors. The stability condition c multiplied by delta t divided by dz is called the courant or Courant-Friedrichs-Levy CFL condition. Also in other fields, so for instance propagation of different waves like in fluids or also in quantum mechanics, similar condition implies the signal can propagate at most than one grid cell per time step, hold for practical all the explicit scheme for any differential equation. So in particular for any hyperbolic problem you will have this CFL condition when we solve the problem explicitly. So what I want to see is to study the propagation of the square wave on a grid, solving using the finite difference time domain technique. As we know, a square wave can be represented as an infinite sum of harmonic components with different frequencies. Especially at this part here, that is almost like a discontinuity, we will have many infinite number of sine harmonica component to describe this kind of discontinuity. And so the square component is very rich in the high frequency component to describe these discontinuities. When such a wave propagates in a dispersive medium, the different sound waves will propagate with different velocities. So we will see some sine wave here basically propagating at different velocity. And the fact that we will have different frequency moving at different velocity will change the overall shape of our square wave. So let's look at the example of a propagation of a square wave using FDTD methods. So in this case, we're using r equal to 1, that is r corresponding to the magic time step, and we know already that there's not going to be dispersion. The propagation of a square wave when delta t is equal to the magic time step is not affected by dispersion. So that means that the shape of the pulse stays in the same as it propagates. So here we have our square pulse at the time equal to 0, and then we update using FDTD MATLAB code, and we can calculate at as it propagates, 100 and 200 delta t, and you see that it propagates to the right, and the shape is not changed. So let's look at when r is less than 1. So we know already that there's going to be numerical dispersion. So when delta t is smaller than the magic time step, we have significant numerical dispersion. That means that the shape of the pulse changes as it propagates. So here we see our initial square pulse, and as it propagates, we will see these ripples that are a consequence of our numerical dispersion. That is just a numerical artifact. And you see that as it propagates, the numerical dispersion also increases. So what happens if we choose r greater than 1? So for instance, our time step that is slightly greater than magic time step. When the scheme is unstable, there is no propagation of our wave, and you see these oscillations that are growing in time. So the scheme is unstable. So the assignment for this module is to implement and test a pulse wave that has a Gaussian pulse, and then we're going to ask you to try different R numbers to see when there is dispersion, there is no dispersion, and when the scheme is unstable. So this was the last slide, and talk to you soon.